Hello, I'm Boolean Algebra and I will be taking you through a small but very important part of digital electronics, that is Boolean Algebra. In this course, we are going to focus on the basics of Boolean Algebra, the postulates and theorems used for simplifying the equations of Boolean Algebra, what are Boolean functions and the basics of logic gates, and finally, some simplification techniques and examples. Okay, to start with, what do you understand by the term electronics? Electronics is something or the science that deals with how to control an electrical energy. As we all are aware of, an electrical energy is transmitted from one node to another node through the flow of electrons. Thus, we can see electrons play a very fundamental role in transmitting electrical energy from the input terminal to the output terminal. The next thing we must look upon is Boolean. Boolean is nothing but a data type having two values, true and false, stating that any output may have multiple combination of inputs but always result in only two possibilities, either true or false. Now these two terms can be directly associated with our third term, that is digital. What does digital do? Digital describes our electronic technology of generating data, storing data, and processing data in terms of two states, positive and negative. Fine. Now here comes the question. What do you understand by positive and negative state? Well, positive state is something where we desire a high output value. Okay, that means logic 1 is desired. We are putting the output at high voltage. Negative state is something where we desire a low voltage output, that is logic 0 is desired. Fine. Now how to match our true and false values with the positive and negative states. It is never true that whenever a situation is true or condition is true, the value has to be positive, and whenever a value is false, it has to be negative. No, it totally depends on the requirement of the circuit. Suppose when we consider the case of positive state, in positive state we desire a high value, right? Logic 1 is desired. In that case, our true situation is equal to 1. That is the value of logic 1. Logic 1, so true is equal to 1. And in that case, false will be equal to 0. Similarly, for negative, what do we desire? A low voltage value. Logic 0 is the desired situation. So, true will be equal to 0 and false will be equal to 1. Now the last term, algebra. Algebra is something that we have studied in our elementary maths and still we continue to this level. It is a set of rules we use to manipulate the symbols and describe different patterns. Algebra, algebraic expressions, what do they consist of? These consist of variables, operators, functions, and they just combine up to form a meaningful expression, isn't it? Now, when we combine our Boolean data type with algebra, we obtain Boolean algebraic expression, okay, which is a combination of Boolean variables, logical functions, and operators, right? So these Boolean variables can be anything, either x, y, anything. And what are our operators? We have basically three operators: and, or, and not. What and is? And is known as logical multiplication, or is known as logical addition, and not is the complementary. Okay, so what can we say? And is our logical multiplication. Right? or is logical sum and not is the complement. Okay, so I think by now you are very much clear what we are going to study in our whole session. Our basic focus, the main focus is on Boolean algebra. Okay. Before getting into detail, we must know who is the founder of Boolean algebra, right? So he is George Boole, an English mathematician. He has given us a set of rules which consist of many theorems and postulates which are used to simplify our Boolean algebraic expression. Now, here I have written of simplification of expression, right? As I mentioned. What does this simplification mean? Why do we need to simplify an expression? For that, let us know from where do we get an expression. A Boolean algebraic expression is basically obtained when we combine all the outputs of logic gates in a circuit in a certain manner using the functions, operators, and the variables. Okay. So generally, what we do, we simplify this expression. Simplifying expression means we are reducing the steps of getting the output. And when we are reducing the steps of getting output, the final output, that means we are minimizing the number of gates. Okay. So we use the simplification technique basically to reduce the number of gates so that we can obtain the output in a minimum number of steps with a more efficient factor. Now also this set of rules add to its advantage one more thing, that it does not change the functionality of the expression. Now what does this mean? It means that we are supposed to reduce the number of states. We are supposed to minimize the gates, but we are not supposed to change the final output. The final output or the desired functionality of the circuit should remain same. So in that case, we need to implement our theorems in a proper way, proper and appropriate way. Let us look into the advantages of simplification of expression. The first one is reduction of gates. Whenever we reduce the number of gates, what will be the other benefits with it? Obviously, the complexity of the circuit will decrease. Okay. Next thing, the total power dissipation factor will reduce. How does it happen? Every gate has its own power dissipation factor, right? So, whenever you reduce the gates, in total, the power dissipation factors will get reduced due to the removal of those gates, elimination of those gates. Also, it will reduce the cost. No doubt, every gate has its own cost. So, whenever you eliminate any gate, the cost of production will decrease. And no doubt, it will increase the efficiency as the time taken by the circuit will be less, the more efficient the circuit will be. Now taking about its functionality, like without any change in its functionality, as I said, this can be more clear to you when you go through your unit 2 and unit 3. For now, you can see the example I have given here. Look, I have considered the first statement. F is a function. F is equal to a naught b plus bc plus abc. Let us count how many gates it has. For this part, if you see, it has two gates. One NOT gate, which is a naught, and a naught dot b. That means one AND gate. So two gates for this part. In BC, we have one AND gate. Okay, and for ABC, again one AND gate. Now these three outputs are put into a single OR gate. So in total we have 5 gates. Fine. Now we have simplified this equation and we have obtained this equation. What it says, f is equal to a naught b plus bc. How many gates have we used here? We have used two gates, one AND gate and one NOT gate. For this part, we have used one AND gate. Okay, and the output of these two are put into an OR gate. So, total we have four gates. So, what happens here in the process of simplification of equation 1 to equation 2, we have reduced the number of gates from 5 to 4. So, our first advantage is verified. Talking about the functionality, you can see this function gives the result f, and even this expression gives the function as f, and this expression also results in the function f. So both the expressions give us the same value. How we have got the simplified equation, I will explain you later in the next unit. But for now, you can see both expressions have same functionality f, and thus the functionality of the expression is not changed. Now let us get back to the very important part we were discussing in our previous points about the positive and negative logic, right? So to just recall once, what is negative logic? Whenever we desire a logic 0 as the output, so our true condition is 0 and false is 1. Similarly, what is a positive logic? Whenever we desire a high logic, that is logic 1, so our true condition is 1 and false is 0. Now here arises a question, why do we need a negative logic? What is the use of it? Well, negative logic is generally used whenever in a circuit we want a particular gate to perform in two different behaviors. Like if I have an AND gate and I want it to perform according to the laws of AND gate in one situation and according to the properties of OR gate in another situation, in that case, we will be using negative logic. Okay. This is basically used in big circuits where transistor logic is used for resetting and setting the circuit. Let us see how do we create this negative logic. Okay. So I will go with the first example. Rest all things will be more clear once you go with your logic gate unit. For now, you just see here. We will take the first example of OR gate. Okay, this is our OR gate. Fine. This is my input A, and this is my input B, and this is my output B. What is the truth table of OR gate? If I have A here and B and my output is Y, what will the truth table is? If I get 0, 0, what will I obtain? I will obtain a 0 net. If I get 0, 1, I will get 1. If I get 1, 0, I will get 1. Again, if I get 1, 1, I will get 1. Why so? Because the concept of OR gate is whenever either of the input is high, we get a high output, right? So we have obtained high output because we have either of the inputs high. Fine. Now, this is equivalent to negative AND gate. Let us see how. We know how the AND gate is, right? This is our AND gate, suppose. I'm taking this, and we have the same inputs A and B, and this is our output Y. This is a simple AND gate. What do you mean by negative AND gate? Whenever we make the negative of any gate, we invert its every input and also we invert the output. Okay. Now in this case, what do we get? This is our A, B, the initial inputs. Then we will get our inverted inputs, that is A naught and B naught, right? Then we will get an invert AND operation on A naught and B naught. AND operation on A naught and B naught. So it will be A naught dot B naught, and finally the output will be inversion of this. Let us take it as Z. Okay, so the final output will be Z inversion. Now let us see what happens. We are taking the same combinations 0 0, 0 1, 1 0 and 1 1. What is the inversion of A naught here? It will be 1 1 0 0, and for B 0 will be 1, 1 will be 0, here 1 and here 0. What is A naught dot B naught? Here we will get 1, here we are getting 0, here 0 and here 0, right? What does AND gate says? AND gate says that when both our inputs are high, then only it will give a high input. So this is what we have obtained the truth table for AND gate. But no, this is not the required thing. What do we require? We have to invert again. There is one inversion of this result. So after inverting, 1 will be 0, 0 will be 1, 1, 1. Now you check. This was the initial set of inputs, okay? And this is our final output obtained. Can you see this output matches with this output for the same set of inputs? So what do we find? This OR gate is equivalent to negative AND gate. So this is how the negative logic works. You can understand these things in a very better manner once you go through the unit 3rd topics. So for now, I think the basics are very clear to you. I will explain you the postulates and the theorems and how do we derive these logic gates in the coming minutes. Thank you.